All right, hello digital crew. Welcome back to another session of Notes with me. We are going to be talking a little bit about some of the things that point to how our universe is expanding. That's going to be through something called the redshift and blueshift. We're also going to spend some time on stars, which is why I wore a nice little star shirt here, right? Captain America shield, but it's a star. Anyway, so let's get into a little bit about light so that we can talk about these two different things, and hopefully from there some of it will be making a little bit more sense with the Big Bang and how we know about it, and also we'll look at stars and just see how cool they are. So on ESRT page 14 you have this spectrum here, the electromagnetic spectrum. And this represents all of the different types of light that exist. So if you look in the middle there, you can see that there is the visible light spectrum, and on one side it is violet, and it goes all the way to red. So those are all different wavelengths of light. They are all waves, and wavelength just means how short the distance is before it goes up down. So the redder it is, the longer the wavelength is, and then if you keep going outside of this visible light range, right, you can see my mouse here, if you go outside of it and you continue to move to the right, you end up in infrared heat. If you've ever seen the movie Predator, that's how Predator sees. He sees in heat vision, which is infrared light. Then if you continue to move, so those wavelengths are getting bigger and longer, right? That takes you to microwaves. And right, microwaves, just like you use to heat up your food. And eventually the wavelengths get so big that they turn into radio waves, which are the same waves that are transmitting sound to your radio. Now let's go to the other side of that. Let's go back to visible light and let's go look at violet. So violet is the shortest wavelength of visible light. And if you keep going shorter, you get to ultraviolet, which is also known as UV, which is something that we get from the sun, and usually people say don't get too much UV light, it could lead to problems like skin cancer and such. If you keep going to smaller and smaller wavelengths, that's usually associated with more energy. So there's less energy with increasing wavelength and a lot more energy with the shorter wavelengths. So from ultraviolet, it goes down into X-rays, which, you know, if you have an X-ray done, they don't just put the silly vest on you for fun. That's to keep you safe, usually to protect, you from taking a whole bunch of it, and specifically to make your reproductive organs safe for sure. And then if you keep going to the smaller and smaller wavelengths, you eventually get to gamma rays, or the rays that the Hulk gets hit with to turn into the Hulk from Bruce Banner, and all that. But those are really dangerous, and luckily we have an atmosphere to get rid of those so that, well, we're not dead. But so there's this spectrum, and it all has to do with how much length there is between the crests or the troughs of a wave. And that's really just what light is, these different wavelengths. So, since we're still talking about light, you probably know if you've taken white light and put it through some sort of prism or a piece of glass, you can get a rainbow, right? White light is made up of a bunch of different colors all together. And for stars, we can actually see that they have different specific lights. Now, there's no maroon colored star or red stars and whatnot, but this is just an example of a color that is separating into specific bands of color. So we're not having white light where it shows the whole rainbow. In this case, we're taking the light and splitting it, and it's turning into very, very specific wavelengths. Again, those different wavelengths correspond to different colors. And based on the colors we get, we can actually tell what a star is made of. Every single element that makes a star gives off a specific signature of these different kinds of light, or different colors of light, I should say. So when you look at a star, if you can separate all these different bands, you actually can learn about the chemical makeup of what they're made of. So this actually does give us evidence for that expansion of the Big Bang. And you might be saying, well, how? You just talked about colors separating. But we're getting to that. So it says here, wavelength of light, or we call them spectra, show dark lines that have shifted towards the red end of the spectrum. So if you look, there is the standard hydrogen, and then there is the hydrogen moving away from a star. So this top black line is if you were in a lab and you took hydrogen gas and you excited it a little bit, you put some energy in it, it would give off this color pattern. Now if you look at the one underneath that, you'll see the pattern looks the same. The only difference is that it's moved to the left, right? You can see that there are those purple lines and they've all moved to the left. Well, actually, hold on. Let me see on the camera. They've all moved to the to my right, your left. So, because the pattern stays the same, we know it's the same element, but because these lines are shifting, it tells us something about the movement. So the red shift, or these lines all moving to the right, or whichever way, to the red side, shows that the light waves are speeding away from you through space. And what that does is it actually stretches out the waves, and it gives you the perception that it's more red than it actually is. So when something's going really far away from you, it is going to have these lines stretch and change the actual wavelength that you see. So that's why on the bottom, even though it's the same pattern, it is red shifted. Therefore, it's probably speeding away from us very fast. So the next one is the blue shift, and it's the exact opposite. So light waves speeding towards you will squeeze into shorter wavelengths, which are then going to appear more blue. So if you look at the stationary hydrogen, which is on top, you'll see that there's a regular pattern. Again, this is what you would see in the lab, totally stationary. Stationary means not moving. And then on the bottom, you can see it's the same pattern, but you can see that it's moved just a tiny bit towards that purple or blue end of the spectrum. So you can see that the red has turned into yellow. You can see that this kind of like light blue, I don't know if you'd call that a cyan, but you can see it's like a lightish blue turns into a like navy blue. You can see that this dark purple turns into a more vibrant purple. So all of these colors have shifted due to this blue shift. So how does this have to deal with expansion? All galaxies, and I should really put a disclaimer, most galaxies, if you look it up, you'll find one or two that actually do have blue shift, but for a majority of all the galaxies we see, they have red shifts. What does that mean? That means all red shift, all moving away from us. So think about that. If everything's moving away from us, it's like an explosion. So that is one of the big pieces of evidence other than that cosmic background radiation that is, supporting the Big Bang idea. So again, if you just look at this, you can see that there's the unshifted, then there's the red shifted, which just shifts a little to the red, and then the blue shifts a little to the blue. Now again, when they are speeding away or if they're coming towards you, it's not actually changing the color. If you were to be like going the same speed with it, it would look unshifted if you were right along with it. But it has to do with your perspective. It has to do with the fact that it's going away from you very quick. So if it's going away from you who's not moving very quick, then it gets red shifted. It appears to be more red, not that it actually is. So here's a video. I'm not going to play it, but you should definitely watch it just to make sure you understand. And also, watch this video. It's basically just a car honking its horn as it drives by, but the same thing that happens with light is going to happen here with sound. If you watch the video, you'll hear the car starts off with a very, very high-pitched noise. Well, it's a truck rather, but the truck is coming towards you and it's got its, horn on. And so that is going to not change a color, but we're talking about sound, it's going to change the pitch. So you're going to hear a really high pitch, and then as soon as it goes past the viewer, who is stationary, you'll hear that pitch drop dramatically. That's why if you've ever watched NASCAR, you just hear all the nyo, nyo, that drop as they go past. It has to do with this same idea that we're seeing with the red shift, blue shift. So here's just a way you could visualize this. If you're looking at the waves given off in a pool by like a little spider or something like that, little bug, all of the disturbances will be equally spaced from one side to another. But if it moves, every time it moves and makes this wave, it's going to scrunch up on the side that it's moving to, and it's actually going to expand away from the side that it's going. So you can see here that A has these bigger gaps compared to B, which has the really, really squished lines. And here's just another visual to see the redshift, blue shift. Kind of interesting. All right, we'll skip through that. Now we're going to talk about galaxies for a moment. So we are in the Milky Way galaxy. It is a spiral galaxy. Fun fact, we've never actually taken a picture of it because the only distance we've ever gone is inside our solar system, and that's a tiny, tiny little dot that's on one of the spiral arms. So if you ever see a picture of the Milky Way, this included, it's not that it's totally fake, it's just that it is made from data. We've never actually just gone up and taken a picture. We just haven't gone that far yet. But one day, perhaps. So, talking about galaxies though. Galaxies are a system of billions of stars. There's the Milky Way galaxy, which is home sweet home, that's where we are. And in terms of the Milky Way galaxy, it is a spiral galaxy. It has tens of billions of stars. It is 100,000 light years in diameter. Just to give you an idea of what that means, I know that we talked about light years in the last video, but 100,000 light years. So that means that if you put a light on, really, really powerful light, on one edge of the Milky Way galaxy, it would take light 100,000 years to get from one side of it to the other side of it. And think about how fast light goes. That's a tremendous distance. So that's the diameter. And then since it is a disk, it's not actually like a sphere. It's only 15,000 light years thick. So the sun is located approximately 30,000 light years from the nucleus, so it's not quite on the outside. It's a little further outside, but it's right in one of those arms. And lastly, just another fun fact, the Milky Way galaxy rotates counterclockwise around its nucleus, and one rotation takes approximately 230 million years. So this thing isn't just staying in one spot, right? Galaxies move too. So again, picture, accurate picture, but guess what? Not taken by a camera. This is some artist's rendition. And yeah, you're here. You're just like a little dot, one little star among the sea of stars that is our galaxy. And then this is a galaxy, and that's a galaxy. Galaxies everywhere. All right, so types of galaxies. You got spiral galaxies, which again is like our galaxy, the Milky Way. It's got these cool little like starfish arms that kind of go around. It's got a nucleus at the center. You've got elliptical ones, which are really just kind of ovally blobs. And then you also have the irregulars. So those can have some really funky shapes, but those are not very common. Really the most common are the spiral and the elliptical galaxies. But really we're just pointing out that galaxies can have different shapes, and they can look pretty cool. Here's the video. You can watch this on your own. It just shows the formation of a galaxy, the gravity that pulls all the gas together and starts to spin, and you can see that's where we get those spiral arms from. Again, you can watch that on your own. And it's kind of following also with star and planet formation, right? That you've got some sort of mass that comes and spins in a disk and eventually does form things in the center due to all the gravity and energy that exists there. So kind of cool that like the big galaxy also forms similar to the smaller thing within it. Just kind of neat how gravity works in that way. So this brings us to stars and how they form. I advise you to please watch this video. I know it's saying like it's not available here, but it's a really, really good video. Guy's got a cool accent. Would recommend. We'll skip past those vocabulary words, but I just wanted to quickly outline some differences between stars just in size. So if you look at this, this is a common type of picture you might see in a Regents exam. I've seen it 2 or 3 times in a very, very similar fashion. And it says that all stars form from nebulas, which are dust and gas clouds. And you're going to form some size of star, which will have processes that, start its light, start its heat. And depending on how big this star is, depends on what happens to it in the future. So if you have a smaller star, like one of ours, I mean, ours is like medium size, but it's not a huge star. If you have one like that, what will happen is it'll turn into what we call a red giant, which the outer part of it kind of just expands out. That will happen to our sun one day. Again, you should watch the video I just talked about. But it just expands and glows, and it starts to cool off. And eventually it lets go of that outer atmosphere, and it turns into a white dwarf. And it just, over a long, long time, just lets go of heat and lets go of energy, and eventually just stops glowing and becomes a black dwarf. No big crazy event. I mean, maybe turning into a red giant's pretty cool, but really, other than that, and letting go of that outside part, turning into a planetary nebula, other than that, it's just kind of turning into a dimmer and dimmer star. Like when you have a bonfire and you let it go, eventually it just runs out of fuel and you just get left with the embers. That's very, very similar to this bottom rung. The difference is when you have a big star. When you have a big star, that's when you get the boom. So if you have a very, very high mass star, what you're going to have is it's going to run through taking different elements and smacking them together in fusion. That generates energy, and it keeps going and going and going, and eventually it gets to iron, which is pretty heavy, and then the thing just implodes and then explodes, and you get this super cool thing called a supernova, which is just a literal explosion of the star, and it just takes its guts and blows them out into space. And those can be extremely bright. Those can outshine a single star, if it's big enough, can outshine an entire galaxy, other billions of stars. So it's a pretty big event. It's pretty cool, and we have seen them. Ancient people have seen them, just looking up and seeing galaxies. I mean, it's awesome. So from there, that could lead to a black hole, or it could lead to something that is potentially part of a black hole, which is a neutron star. So this neutron star is something of incredible mass, just in a very small volume. It's very dense. So what I mean by that is like dense, right? Like dense materials are really hefty in the hand, right? Like a piece of metal has a lot of heft in your hand. You can feel the weight of it. Now imagine that you just keep packing mass into that same small thing, and it just feels heavier and heavier, even though it's the same size. That's a neutron star. They're extremely dense. And then we're going to talk about black holes in a moment. So here are the notes for stars, though, and especially the top. The top has a lot of good stuff here. So stars begin as nebulas, these huge masses of gas and dust, and the way that they form and really start getting going from this cloud into a star is by compression. So compression, if you've ever worn compression socks, right, compression is a squeezing force, right? Those compression garments, they all squeeze onto you. It sounds weird, but that's what they do, right? So compression by gravitational force. And so when all this gas and dust come together, eventually the gravity gets so big that the temperature rises, right? They're being squeezed, and if you squeeze your hands really tight together, you can feel that heat. So it's going to increase the temperature, and eventually you get the process of fusion. So what is fusion? Well, nuclear fusion is a thermonuclear reaction, and the part that you need to know is that hydrogen, which is a very, very simple element, the most simple element, is going to, two of those are going to get knocked together and fused, which means that they become one, right? And it's going to turn it into helium. So when you have two hydrogens, it's going to squish together and turn into helium. This is not a simple thing. We don't really do this kind of thing on Earth. It's hard to achieve. Really, you need high temperatures, high pressures. Fusion is a thing we're playing with in technology, but once we figure out how to do it, we'll have like a lot of energy. Anyway, point is, this is an intensive process. I mean, think about it. This is the thing that brings us the sunlight, right? And that travels really, really far and has been burning a long time. So that is nuclear fusion. So types of stars, there's the main sequence. These are the most common form of stars. And then they are going to cool down and they're going to form the red giants or the red supergiants. Depends on which way it goes, like we saw in that last picture. Then you've got the white dwarf, which is left over from the red giant. You've got the neutron star, which we talked about. You get that after a supernova. There's notes on the supernova that when the star explodes, lets out its guts. And then also, just as a quick fun thing, you might want to look up some videos on this, but pulsars, they are an interesting type of star that spins and lets out these pulses of evenly timed light. They've actually helped us a tremendous amount if you're really, really interested in looking up stuff about space. They've helped us a lot with figuring out space distances. So if you are interested in looking stuff up about pulsars, go for it. So what's a black hole and how does it work? So we've got a couple images here taken from some, cartoony mainstream content. You got like Kirby, you've got a Dota move happening in the top right, which is a video game. You got Bugs Bunny, you got that cool frog guy. How does a black hole work? What is it? So in class we talked about this, and each class I ask usually agrees that it's probably something similar to Kirby, and I have to agree, right? Kirby doesn't get any bigger. It all, just kind of goes somewhere. So how does that work? So black holes are pretty neat. We think that, and we strongly think that, there is a huge mass in the center, and it's really tiny. So similar to that neutron star that we were talking about before, where it feels really, really hefty in your hand, right? But just keep adding mass and keep going and going and going. Well, what if that just kept getting enough mass to the point where, it wasn't growing and it had enough gravity that light couldn't escape? It just literally was stronger than light trying to get out of its reach. Well, that's a black hole. So what you see right there with this black boundary is not actually a solid thing. What it is the zone where just light does not escape from. So in the center of this is a smaller thing, a much smaller thing, and that is where all that gravity comes from, and that's where that power comes from, and why it is sucking all those things in, because it's just an incredibly high mass that is pulling everything into the center. But we are not near one of those. We don't have to worry about them so much. But we do have a supermassive one in the middle of our galaxy, so that's kind of cool. All right, and then the last slide, the HR diagram. We've been working with this now for about a week, right? You did the gizmo on this. There were 2 worksheets. We went over one recently. So HR diagram is a chart representing stars' brightness and their temperature. And here it says absolute magnitude. What does that mean? Well, absolute magnitude is its actual brightness. So if you looked from Earth and you took a telescope and looked at all these stars, you might look at this chart and say, well, I don't know, Betelgeuse doesn't look as bright as the sun, right? The sun is the brightest star. Why is it in the middle? That's because that's a relative brightness, right? That is because we are really close to it. Any light that you bring closer to your face is going to seem a lot brighter. So these are the actual absolute brightnesses that each of these stars has. So if you're talking about all these different stars, you want to make sure that you're comparing them not based on what we see from our distance, but what they actually should be if you were equal distance from all of them. So that's what this is showing. This is showing their actual brightness if we were an equal distance to all of them versus the temperature, and then it also shows us the color, and if you look at the right hand side, it shows you where to see smaller and then more massive stars. So we've worked with this quite a bit. It's on page 15 of ESRT, and that's pretty much it, right? We've got the 4 different groups: main sequence, the giants, the supergiants, the white dwarfs, right? And underneath it, make sure you also remember it shows the stages. So all the younger stars are main sequence, then right they go to giants, supergiants, and then white dwarf is like a late stage star. So that is it for today. That's it for stars. That's it for Big Bang. We will be next talking about planets. So stay tuned.